Hello everyone, welcome back to channel Class Cabo and welcome to my video. My name is Mufty Putratama Sumarto. I'm from Electrical Engineering of Universitas of Indonesia, and today opportunity I will try to explain in this video about propagation and Potlatch model. Okay, let's go jump through it. Uh, First of all, the table of content, the outline we're going to discuss today in this opportunity. There are four main points. The first one is signal propagation characteristics, and then we go into the path loss models, and then we get a little bit discuss about the millimeter wave, and we'll discuss another model that is empirical channel. Okay, so let's jump to the first subject. It is propagation characteristics. Okay, basically, we departure from a direct and multipath propagation. It is one of the TX and RX signals, and then from the procedure, it appears have three main problems that I want to include in this material. There is fading, path loss, and shadowing. Basically, path loss is like an average shadowing that is basically due to obstruction, and then we have fading and also shadowing. These three problem needs a solution, that is a propagation characteristic. So uh, the conclusion is the wireless communication need a propagation characteristic to prevent effect of fading, effect of path loss, effect of shadowing, or even Doppler spread. Because basically wireless communication system provide a high noise channel that uh, these these three problems uh, is feasible to occur on term of wireless communication. So propagation characteristics is needed on wireless communication. Okay, so to the second material, there is path loss modeling. The first one I write here is Maxwell equation. But I think it's very complex. It's not impractical. So we jump because it's too complex. It have another model. It's free space and two path models, but it is too simple. So we jump to the next one is ray tracing models, but it requires site-specific information. And then we go to the measurement-based answer model. It is not so accurate. It is used to access different design. And last one is single slope path loss exponent model. It is good for high level analysis use. Okay. Now, I think I will tell you more about two model. Describe the first one is free space or LOS model. As you can see, the system is D V times D. It's power falls off due to effective aperture of the antenna, and also path loss for unobstructed LOS path. So we discuss the first one first. The power for falls off is proportional to 1 per distance square, and it's also proportional to lambda square. Basically, it is inversely proportional to f square or a frequency. But if you look at the next model, the two-ray model, the path loss for one LS path and one ground constructed bounds. The ground bounds, approximately cancel LOS path above critical distance. But you can have the criteria for the power falls off too. the power falls off in this model is proportional to small d square, the distance. It's proportional to the d square, and then it is independent uh, independent of lambda value. So the two path cancellation are equivalent to two element array. For example, the effective aperture of the receive antenna, so it will change. Okay. Now, I want talk a little bit about the MM wave. I think what is a big deal, why we use it, and what is it. Okay, first we start from what is MM wave basically. It is the band of spectrum with wavelength between 10 millimeters or 30 gigahertz and 1 millimeter or 300 gigahertz that can be used in broad range of products and service. I think it's many services. So now, how does mmWave works? mmWave technology aims to greatly increase the amount of bandwidth available on a specific part, like I mentioned before, 10 millimeters and 1 meter of the radio frequency spectrum, and it will extend it a much higher frequency band. So, why do we need that? Why do we need a technology that use specific part of it and extend into much higher frequency band? The answer is it is made us to use it for IoT device. I think it's specifically a simple IoT device. It will enable us to use higher data rates. It will increase the number of access point and will also facilitate the reuse of channel across the WLAN coverage area. So I want to talk about another thing is mmWave propagation. It is channel models is immature based on measurement, few accurate analytical model, and then the path loss proportion to the lambda is huge, and it's also have oxygen and rain absorption. MOM system will be short range or require massive MIMO. Okay, so that's it all about mmWave. Now to next to the empirical channel models. First, we look back into the early cellular empirical models. The whole model's work principle is based on extensive measurement. Example, this is the example of Okumura model. This empirically based site of frequency specific. This graph Hata model is analytical approximation to Okumura. The COS231 model, it's extend Hata model to higher frequency, multi-stop model, and then Wolfish or Bertoni model that extend cost 231 model to include diffractions. Now we jump to the current model where we have LTE and 5G. It details path loss models for UE and base station for different multipath delay spread, user speed, and MIMO antenna correlation. Now, the developers already make the 5G model includes higher frequency up to 100 gigahertz. Now, we go into the Wi-Fi channel models. They are TGN and TGAC. It is indoor and outer path loss model with MIMO 4x4 and greater, 40 megahertz channels and greater, and different multipath delay spread. It is commonly used in cellular and Wi-Fi system simulation. Okay, so that's all for me. I try to want to summary all of the topic we've been discussed in these videos. The first one is the models that has been discussed. It's vary in complexity and also the accuracy too. The power fall off that that is already explained in the models is proportional to the distance square free space, and then the MM wave propagation model still immature because the pet loss is too large due to frequency, rain, and oxygen, just like I said before. And the empirical models is used in simulation. So, that's all. Those conclusions should be a closing statement from me. I'm sorry if I have a lack of information for this material. I hope you get the benefit from watching this video. I'm sorry if I have a mistake. Thank you again. See you in another opportunity. Goodbye.